Yeah, so my name is Oleg, and I'm going to tell you about language in autonomous driving. So let's start with this kind of main question: why would you use language in self-driving? That was actually completely non-obvious just a few years ago, right? So it all started at around 2018, actually, with a Berkeley Deep Drive X dataset. It's the first explainability dataset for self-driving. And in that first paper regarding explainability, this is a citation from that paper, they cite those main three reasons why would you need language in self-driving. First is user acceptance. Self-driving is a radical technology, so everyone needs to trust it. People need to understand and extrapolate the behavior, and also effective communication between the vehicle and a human. Then another thing is that before, let's say 2023, there was the main reasoning architectures before LLMs were mainly those kind of technologies. You guys are probably all familiar with Monte Carlo tree search. There are also a lot of planning in deep learning using graph neural networks and a mixing of semantic engines and deep neural networks. But in 2020, there was this discovery where just next language token prediction can make model reason. And this is GPT-3, not 3.5, where already in 2020, it can do very simple reasoning regarding self-driving, right? So you can see that I'm on the 3-lane road. In the middle lane, I need to turn left. And what do you need to do next, right? And it auto-completes this plan. And this plan kind of makes sense. Yeah, there is a small mistake, but it's kind of okay for 2020. But think about it. It's completely non-obvious. Why would next token prediction make any model to reason and plan? Right. So when I've seen this, I finally realized, all right, so then this is a technology, language model technology, is the one that would allow models to do planning and reasoning in one single architecture without any extra machinery like tree search or GNNs and so on. Another insight is that explanation is actually kind of equals to reasoning, right? So think about it. Imagine you see a person and then you press on the brake and then the model generates explanation. Okay, I'm pressing on the brake because there's a person on the street. Right? So if you just do this in codes kind of simple thing where you place this explanation before you do the action, suddenly the sentence becomes a reasoning sentence where you say, okay, I see the person and I'm pressing the brake because there is a person on the street, and then you press the brake. Right? So the single thing that happened is that you kind of swap the places here between explanation and action. And obviously explanation now don't have access to action. It's kind of a bit tricky. But you can see that explainable model actually is a reasoning model, which is kind of non-obvious fact that became obvious when LLMs kind of came on the scene. Okay, so yeah, another thing is language is a very nice compressed information medium. So take a look at this very complicated scene in central London. While it's all complicated, it's actually quite, it's not so long to just make a really nice description in text about all of that. My lane is straight only, the light is on my lane is green. I'm just attending to pedestrians, speeding it up. If you just compute those words, it will be like just 140 bytes, right? Which is it's kind of cheeky information compression, but that's pretty much everything you need to drive in the scene. And because it's such a nice information medium, there was this whole field emerged about that is called LLM agents that take language and use it in all sorts of different ways, right? And we in self-driving also can use all technologies from LLM agents to endow our models with those many advanced features that take advantage of this medium. You can have long-term memory, in-context learning, lifelong learning. You can interact with the user, obviously, and I'm going to show examples of all of that. And the last but not least is that edge case data for self-driving is particularly precious to actually drive well, you need a lot of combinations of different objects and a lot of weird things going on. So people behaving weird, some animals on the road and so on. And before a large pre-trained models, it was kind of non-obvious what to do. So you just, as a company or a lab, you have to collect all that data. But now, with the release of all that huge models that we can all use, hopefully they're still open source at the moment, right? There is like the second option for many robotic labs and companies. So before you have to collect this data yourself, but now you can rely on the large models that are pre-trained on that data, and you hope that you're just going to generalize to those driving cases. Okay, so then how would you add a language model into autonomous driving system? So for that tutorial, I reviewed many papers, and I'll share the slides later. So like there are a lot of links just to show that there are a lot of work actually going on in that field. And I mainly picked some papers which are about pre-trained language models and that appeared after 2023. But this is the prototypical system. How would you do that? So you take the input from kind of autonomous driving sensors. So it could be multicam vision or just scene state, LiDAR information. You pass it through this language bridge, which translates this information to tokens. Then you use a pre-trained language model, and you pass the output of that through another action bridge, and that makes a driving output that you can pass to the car. Additionally, you can have a language output, which obviously tells you explanation and reasoning. And then on top of that, you can add a lot of agentic infrastructure from LLM Agents field, and I'll show you different examples. But before that, how can you measure? So before implementing anything, right, you want to establish a nice metric. So the first thing to do is obviously how well it drives. And there are several simulators like Carla, new scenes. There are new upcoming nerve simulators that Nikhil was talking about. There's a high-end environment, which is simplified simulator. The second thing you want to do is to measure how well vision and language work together. And for that, there is this beautiful picture on this Drive VLM GitHub, as you can see, where they show all sorts of data sets that test video to language conversion. Specifically, it could be VQA or explainability. Here's the BDDX data set. There is also a Lingo QA data set that Wayve released already. And one specific thing that we also released is this new technique where to test how well model answers a certain question, we train yet another LLM as a judge that just predicts correctness score. Because when we started to work on VLMs, we found that typically used metrics like Meteor, Blue, and so on are not really capturing all the semantics for self-driving. They're capturing the sentence structure, but they often lose the nuanced meaning, like, okay, was the car actually left or right? Like one word can matter a lot in such scenarios. And we found it a kind of a fruitful approach where you just actually fine-tune yet another LLM to compare between VLM answer and a human answer, and then just gives you a score. And we released the paper on that, so you can read about this, and it leads to very nice correlation with humans. So another thing you want to measure, which is very non-trivial, is the whole alignment between vision, language, and action. So if you think about like three modalities, actually, so it's not only visual and language, but it's also action comes in, and it's all happening in a closed loop. And it's very tricky how to measure all those capabilities. But there are new benchmarks coming up. So there are at least three I listed here: LangAuto, LangPilot, and Dorothy. And some of them measure instruction following. Some of them measure reasoning in a closed loop. So you can check them out. All right. So just kind of a division of all the work that happened in LLM-based driving. The initial papers that appear, they mainly focus on this agentic infrastructure, where originally there was no really many strong VLMs, visual language models. So people used ChatGPT using API, just trying to play with this idea of how to use language for driving. And in this picture, I'm kind of labeling in green like amount of focus or amount of research that was put into one of the aspects of that driving. So you can see that in those papers, majority of work was put in agentic kind of LLM text-based infrastructure. So here are some examples. This is the earliest paper I was able to find, actually. It's called Drive Like a Human. And in that paper, they use this highway environment. They take observation from different lanes, put it into text, and let ChatGPT reason about it, right? So ChatGPT can generate different discrete actions in text, and then you parse that and you put it back. And even already there, quite some time ago, actually, it was like in the summer 2023, they already did very advanced kind of reasoning techniques with memory. So you can see that, okay, so you see those two cars, and first ChatGPT answers, okay, I want to just stop and wait for other vehicle to pass, but in reality, you can just go because there's not a gap. They implemented self-reflection where there is a human kind of correction for that reasoning, and then GPT reflects on that, saying that, okay, well, there was enough space that is added into the memories, and then later that next time you see the same kind of situation, you use that memory, self-reflection, and so on to correct your decision and actually implement the correct driving decision. So you can see that this is very sophisticated reasoning already happening with very early ChatGPT models just using API. And a few other papers along those lines is, so for example, Agent Co-Driver. Here they added yet few more advanced features. For example, they added a module so that you can communicate with words with other vehicles, which is, again, it just takes advantage of the language being this very nice compressed medium. You can just say to everyone else saying, okay, I'm just changing lanes to the left. And other cars being also autonomous driven by LLMs can understand this and react appropriately. And you can see that there are quite many features this paper introduced. There was a memory and lifelong learning, self-reflection, verbal communication with others, and chain of thought. Yet another paper along those lines is called Language Agent. Used another technique from LLM agents, which is usage of tools. Specifically, they had several tools available to them. For example, you can get a leading object or some kind of predictions, and then take decisions based on all those tools. Use some kind of reasoning, and even use retrieval augmented generation, where you use some kind of embeddings to get the most common text descriptions of the scenarios that you have seen in the past. So next set of papers focused on kind of the right part of this diagram, where instead of focusing on agents, people focused, okay, how can you transfer action? How can you parse action from LLM into driving output? And this is a non-trivial problem. So first papers were just trying to parse very simple discrete actions. But here I just found a few more advanced papers. For example, Language MPC is the one that I quite like. Is a paper where LLM actually controls parameters of MPC controller and can take this high-level decision like tuning coefficients for MPC. And specifically, when you do this, you get those advanced features like driving style adjustment. For example, you can say in a pre-prompt that, okay, I'm an aggressive driver or I'm a conservative driver, and deciding LLM would appropriately tune the parameters of NPC and do kind of appropriate behavior. And another interesting two set of papers, LangProp, actually from Wayve, from Shu, our intern, and LM Pilot, they went into another kind of approach where LLM generates code that is then executed on a closed loop simulator. So instead of generating simple decision, you generate the whole procedures, which is a very interesting idea. All right, so then after that, several VLMs appeared, and here's a small review of those papers. This is the kind of the general architecture of VLM that drives a car. So here, instead of text, you actually have vision that goes through vision token bridge, and then later goes through vision language model and some action. And in those papers, people did not really focus on this agentic infrastructure, but mainly focus on vision. So this bridge is the main kind of focus of the research in this area. So here is a few papers that I selected. First is Drive GPT-4. And here we can see this typical scheme where you take in frames, you use visual encoder, and typically what's used is clip, like everyone else. People found in self-driving that, okay, well, the best visual encoder that transforms images in text is clip. Then you take that, you have a learnable projections, which generate tokens for large language model, which you can train or fine-tune with LoRa, or just freeze and just fine-tune projections. And using that, they got state-of-the-art on BDDX. So this is where we first have seen that large language models get state-of-the-art on explainability data sets. All right, so we also at Wayve had a very similar project, very similar idea, which is called Lingo 1. So we released actually an academic version of Lingo 1 in the paper Lingo QA, and architecture in that model is very similar. Also, we take images, pass it through clip, pass all that through QFormer, and have a large language model. Specifically, the best was Vicuna. With that paper, we actually released the data set, training data set. We released Lingo Judge that I mentioned before, and various just ablations of very different parameters that you can tune here. And here's the demo of Lingo 1. This is a more kind of sophisticated version, but I still can participate in a dialogue, so I can read here. So user asks, what's the weather like? And Lingo says it's rainy. Do you drive differently in the rain? Yes, I need to be more cautious due to rainy conditions. How come? Due to rainy conditions, the road might be slippery and visibility might be reduced. So when will you go? I'll go once the black sedan in front of me start moving. So you can see kind of scene understanding here. And then it kind of goes into this generic rant, right? So when will it stop raining? It says, I cannot predict. So is it true that it always rains in London? And it says, no, it's not true, which is actually correct. Today was a sunny day. So the next section of papers are like a set of papers that focus on perception. And in that set, people focused mainly on how can you generate not only language, but also additional perception output. And typically it would be bounding boxes or segmentations. So in that approach, those two areas where how can you put kind of vision into the language model such that they can predict bounding box segmentation are the main areas of research. And one of the most advanced one that I found actually is this paper called Embodied Understanding of Driving Scenarios. And the guys here trained on many data sets. Well, data sets included Nuisance, Waymo, 3D, YouTube, and so on. And it's actually quite sophisticated architecture that involves this idea of time tokens, such that a model can have temporal predictions, not only responding to what it sees now, but also predicting the future and refer what happens in the past, and also generate some perception. So here are, in my opinion, quite sophisticated examples of what it can do. So for example, you can ask, what's the 3D spatial location at a certain pixel 2 seconds ago? And the model correctly predicts what happened at that location, and it was a pedestrian at that location, so it identifies a pedestrian and says where he was. It can do also regular action decisions, so you can just query by a bounding box what do you need to do for that specific car, right? And it's correspondingly figures out that where this car is located and what to do with it. And it can do 2D to 3D kind of a transformation where it clearly shows that it understands 3D world. It becomes really sophisticated perception system. And another paper I wanted to highlight is called HILM-D. And the main challenge that they addressed is that in self-driving, as opposed to like many generic video understanding systems, you really want to pay attention to small objects, which are very important. And those are traffic lights and traffic signs. Those are typically quite small. They could be far away, but you want to really, you never want to ignore them. And that specific paper focused on a vision system that has 2 different branches, so with low resolution, high resolution videos, such that from really quite far away and like using just 1 pixel, they can predict that there is a red traffic light. You can see like a very small bounding box here. And hence it's a very nice solution to do this kind of detailed perception. We also at Wayve played with that idea of referential segmentation, and what we did, we attached a segmentation model to Lingo 1. And this is a small demo of this. So you can see a user is asking what they're paying attention to. And the model not only responds to that, but also identifies 2 regions, A and B, as a segmentation masks, and says that I'm paying attention to drivable area and the traffic in front. And then you can ask even more stuff, and it says, okay, well, now I'm paying attention. So you can ask about objects in the world, like what are the broken white lines mean? And you've seen that it selected the lines correctly and predicted what it is. All right, but the most interesting models, in my opinion, are the models that actually can drive end-to-end in a closed loop and use visual language. And for that, just small digression is that if you think about it, why do we trust human drivers to drive a car? If you think, so humans are they just pass a theory driving test that takes at most 1 hour in some countries, in some countries even less. And pass a practice driving test, which also at most can last 1 hour. And if you think about it, this is way less than what we do in the self-driving companies, where we test every model for orders and orders of magnitude more than 1 hour. And obviously right now VLMs can just go and pass a driving test. It's been shown a few times on YouTube. You can check out the GPT-4 passes driving test. So why do we trust humans? So the one thing is that humans share all common knowledge with us, right? So like other drivers share knowledge with us, so we trust them. For example, we don't allow kids to drive. But now you can see VLMs have that knowledge now, so we should kind of trust them more. Another reason that humans can explain decisions. But this is actually a bit misleading, because if you have a VLM that just explains decisions, it's not obvious that those explanations actually relate to actual action that the model took. So you just have like two robots speaking. One is driving, another one just tries to explain what's happening, but it's not clear that explanation is related to the action. So the reason we trust human explanation is that we know that it's all in the same kind of brain and same substrate, and it's all happening in a closed loop. And this is, I believe, the main kind of the ultimate system where the system can predict, explain, and so on, and drive together through the same weights, through the same network. And those are the VLM-based papers. One of the early ones is called Drive Anywhere, where researchers use the, again, very similar idea of a VLM, and well, it's mainly clip-based kind of model, but it actually was tested on a real car where the network actually predict control signals. Another very great paper along those lines is called ML Drive. I already mentioned that. So here, this is this prototypical system where you take in video, again, for the very similar clip and Q-former and so on. But then also you generate tokens of actions. And then what you can do is that you can test it in a closed loop, which those guys did. So yet another innovation of this paper is that they also took LiDAR input and put that into the LLM. They use specific pre-training kind of step first to align vision and LiDAR to just get a nice visual features, and then put it into language model. So you can see people started to like test those models in a closed loop, generating actions through the same weights. Another interesting one is called ADH, and here you can so here the original idea is that there are actually two models. One is a high-level VLM that can do reasoning and has way more parameters, so it can go answer questions. But then what happens is that model modulates another low-level controller, which is also a VLM, but it's way smaller, so it can go and drive a car. So specifically here, it predicts waypoints. So it's like hierarchical architecture, but also can drive closed loop. And we at Wayve recently released this Alingo 2 model, and this is the first language model that ever drove on just real public streets, right? So it's been tested in the real world. You can see the text it generates is kind of explanation of its actions. And in green, you can see the trajectory that it takes. So it's first a VLM that can explain itself, but also take action through the same weights, right? And this is hopefully leads to better alignment and explainability. All right, this is kind of very high-level training recipe of Lingo 2. So first we pre-train a vision model, then we align language and vision, and later, obviously, we add action through our own kind of driving processes, and we get a full model that can do language, obviously vision, and then driving. And the last paper, but not least, just very fresh. So recently, our intern Catherine released a model called Karlava, and we got the first place on a Carl Autonomous Driving Challenge with that. And this is also based on a language model, specifically Llama. And this is a small demo of that. So you can see this is also a model that can go and drive a car, just goes for some tricky situations. And there are two flavors of that model. One doesn't use language, one does. And this is the one where it generates language. So you can see it auto-regressively generates trajectory and then language token. So you can see highlighted explanations here. Just scroll down a little bit. Oops. Yeah, so you can see pedestrian, it highlights the pedestrian. And then it correctly identifies construction sign with explanations below that it's going to go and go around it. So you can see the demo later. All right, so as a conclusion, so first of all, there are a lot of unsolved problems. So this is all work in progress, very fresh field, LLMs and autonomous driving. There are measurements problems. We don't quite know how to robustly measure vision, language, action alignment. There's not a lot of high quality vision text action data. It's mainly auto labels, not human labeled yet. I'm not aware of like any big human label data set. So Clip is not really great for self-driving. One of the lessons is that we would love to have one of the lessons of our team is that it would be great to have a model that is really good at spatial reasoning, whereas Clip is more like sometimes acts as a bag of words, right? So we just want something spatial and can reason in language. Also, large language model is not super efficient, right? So you don't want to run like 70 billion parameter model on the car. So there's a lot of work needed for efficient inference. And in general, there is not yet like one big model that has agentic features and can drive end to end. This is like a small table I made. So in green, it means that some feature is implemented, and you can see there is no single column that is all green. Specifically, features are closed loop evaluation, can run a real car, can participate in a dialogue, referential perception, agent capabilities. So far yet there is no single paper or work that can cover everything and be like this holy grail of LLM, visual LLM in a self-driving that can do all of that together. All right, and just final thoughts, like just hand wave argument kind of for LLMs and self-driving. So before so there's always this question in the field, like, do you need AGI for self-driving, right? And there were always two camps, and there was like really no winner, right? Some people say like, okay, you don't really need any human level intellect to drive. It's too far away anyway. We can't afford it. And maybe self-driving is like a narrow task, right? So it was called narrow AI, right? But people who argued for AGI, the good arguments are that roads are actually designed for humans. So it's better to have human intellect. Well, another good argument is if you do solve AGI, then driving is like an easy problem. And if you think about like a lot of edge cases that happens during driving, you know that humans actually they use all the intelligence they have sometimes, right? Sometimes people drive reactively, but sometimes you need logic and so on. But after 2023, some of the arguments on a camp without AGI kind of went away, right? So first of all, AGI has become like closer and closer. And we have a lot of release pre-trained models, so you don't have to solve it yourself, right? So hence, I think it's a good idea to like jump on this train and claim that yeah, we actually do need AGI for self-driving. So let's try use this technology VLMs, which is kind of the closest we have for self-driving. Yeah, thank you. That's the end of my talk.
Hello, can you hear me now?
Yeah. Mm-hmm.
Okay, so I would like to know regarding the LLMs. So as you know, LLMs hallucinate. So when we use them for reasoning and based on that, we are trying to utilize for like we are taking that as a prompts for driving capabilities. So what do you think about the safety implications of that if they, let's say, hallucinate about something that can actually make the driving maybe unsafe for humans. So what do you think about that? Yeah, thank you.
Yeah. Yeah, so as I said, mixing LLMs and in autonomous driving is a extremely, early field of research. So we kind of don't know the answers on those questions. Everyone in the world tries to reduce hallucinations. So one cool thing about using pre-trained LLMs is that you kind of piggyback on a lot of other researchers trying to solve problems for you, right? So instead of trying to solve it yourself, you know that, okay, a lot of people working to make LLMs hallucinate less, right? And so another kind of view is that no matter what, you want to have really robust testing infrastructure for all your self-driving models, right? So we at the companies, I mean, since we're doing end-to-end driving, we have to have very robust testing infrastructure, off-road evaluation, like in neural simulators and on-road evaluation and so on. And no matter what, whether we use reasoning or don't, we have to have that done, and hopefully that catches all the regressions possible, right? So we're really investing into all sorts of evaluations, but as I mentioned, evaluations is not really yet a solved problem specifically for LLM. So there's not much work done on like reasoning, for example, hallucinations and self-driving. I'm not aware of any good benchmark yet. So yeah, the single, it's not a great answer, but yeah, it's a kind of work in progress.
Yeah, thanks for the talk. So actually, I have a question. So nowadays there is another like route way it's just using the word model things, right? So in terms of this VLM strategies, compared with the word model strategy, what do you think? Which one? Yeah.
Yeah. So well, I mean, we are pursuing both of them at the company, and obviously, even Gianluca presented this paper where people started mixing those, right? Where a single model can generate language and video at the same time. So there are ideas of putting it together and try to take advantage of both models, right? So there are papers, I forgot already the name of it, claiming, okay, you can do reasoning in the visual space, right? The fact that you can predict the future and you can predict different futures, this is how Monte Carlo research even right, works, is that by predicting multiple futures and figuring out what's the best one, it's also certain, well, it's a reasoning, right? It's a planning and reasoning kind of paradigm. So there's definitely a lot of ideas how to mix them together, and I don't think they are, they're complementary, right? I think there's definitely a lot of research to be done. How do you do visual reasoning and language reasoning at the same time? And in fact, this is what humans do, right? So humans can imagine futures, but also humans can reason about future in words, right? And all of that obviously is beneficial.
Thank you for the great presentation. I have one question. So the chat box of the LLM to respond to the user to indicate how does the vehicle thinking is pretty interesting idea. Just thinking about instead of just responding to the user, will it possible that the user prompting will potentially affect the driving of the vehicle? So for example, if the user prefer driving in the highway instead of local road, prefer to drive in the middle of the lane instead of the carpool lane and the rightmost lane, would that make it possible to interact between the user and the vehicle itself?
Yeah. And so I'm going to publish the slides, and there is a list of papers, and some of them actually explored that exact idea. Not exactly the example that you're saying, but the idea of instruction following, idea of interaction with users, specifically those papers that focused on LLM part, not the VLM part, because unfortunately, I mean, still we still don't have good papers on VLM agents, right? On visual agents, but there are papers exploring exactly those ideas. Yeah, and answer is yes, it's possible. People demonstrated that, and yeah, hopefully that's the future, right? So you can change the style of driving. Say, okay, I want to drive more maybe safely or aggressively or stuff like this, right? You can even instruct, okay, you have to go left or right, and all permutations of that.
Thank you so much. I'm really looking forward to the papers. Thank you.